Welcome back to the deep dive. For years, we've talked about large language models, LLMs, as these fantastic text generators.
Right. For writing marketing copy or maybe that null you've been putting off.
Exactly. But today, we are leaving that world of abstract language behind and diving into something far more structural, far more rigid. We're talking about hardware engineering.
It's a huge shift. I mean, the sources we've analyzed show LLMs becoming these core collaborators in designing the very chips, the silicon that power our world.
And traditional hardware design is notoriously difficult.
Oh, it's immensely complex, it's expensive, and it's a huge bottleneck in development cycles because it demands such deep, specialized expertise.
So the LLM isn't just a fancy search engine here. The research calls it an engineering co-pilot.
That's the perfect term. It's a force multiplier. It's designed to augment human knowledge, not to replace the brilliant minds actually doing the work.
And our mission today is to move past the theory and get practical.
Right. We're going to unpack a specific case study that shows this in action. The complete design of a low discrepancy sequence generator.
An LDS generator.
Written in System Verilog, which is a highly complex hardware description language.
An LDS generator. That sounds pretty academic.
Yeah.
Why was that chosen as the guinea pig for testing out an LLM?
Well, there are three main reasons, and they were all highly strategic for the research. First, it relies on really clear algorithms.
Okay, what does that mean?
The math behind sequences like van der Korpet or Halton is precise, it's formal. And LLMs, with their ability to model that kind of mathematical structure, are excellent at implementing them correctly.
And the second reason?
The design is inherently modular. It breaks down cleanly into these independent building blocks, which is just ideal for the iterative, prompt-driven way an LLM works.
And maybe most importantly, it has a practical application. This isn't just some toy project.
Not at all. LDS generators are essential. They're used in everything from computer graphics and calculating complex integrals to running Monte Carlo simulations.
The kind that predict weather patterns or financial risk.
Exactly. So if an LLM can reliably build this, it proves its worth in serious engineering.
Okay, let's unpack this shift then, because generating a coherent stream of ones and zeros that actually describes a circuit is 1,000 miles away from writing an email.
It is, and that brings us to section 1. How we get from general capabilities to these highly specialized domains. The research identifies 3 key ways LLMs are getting into the hardware design space.
The first one sounds like the LLM is basically learning to speak the technical dialect of a chip designer.
That's it, cross-domain penetration. This isn't just syntax, though. It's the LLM showing it can understand the semantics, the conventions, the constraints of specialized code like System Verilog.
So it's not just knowing the words, it's knowing what they mean in context, like clock domains and reset logic.
Precisely. And that capability just completely changes how engineers spend their day.
Which is your second point, right?
Yep.
Reshaping design workflows.
Yeah. By automating the grunt work, the hardware description language, or HDL, code generation, and by handling the often fiddly automation scripting, LLMs just massively increase efficiency.
So all those little scripts engineers hate writing.
The LLM handles that, and that dramatically accelerates time to market.
And the third way is like having the instant, always-on expert in the room with you.
Intelligent decision support. The LLM acts as an instant resource. It can explain complex concepts, recall tricky syntax, suggest design patterns, all on demand.
So it helps veterans, but it must also be a huge leg up for new engineers.
It democratizes knowledge. It's like having an entire library of textbooks memorized and perfectly indexed.
Okay, so we know the why. We know why LLMs can play in this space. Now, for the really interesting part, the actual process. This isn't a one-off prompt. This has to be a robust, multi-stage collaboration.
It has to be. And the case study lays out this complete 6-step LLM-assisted workflow. It's key to remember the human engineer is always the final arbiter. The LLM is just providing leverage.
So where does that journey begin? Step 1.
It starts with requirements and analysis. The engineer defines the basic problem, but then uses the LLM to really solidify the design specs.
Like a brainstorming partner.
The ultimate brainstorming partner. It helps research potential implementations and finalize the mathematical approach before a single line of hardware code is written.
And once we know what we're building, we have to decide how to break it down. Step 2.
Interactive architecture design. This is where human expertise is absolutely crucial. The engineer guides the LLM, defines the system architecture, partitions the modules, sets up the interfaces.
The human provides the blueprint.
Exactly. The LLM excels at implementing an idea, but the human has to provide that initial architectural vision.
Then we get to the part most people think of with LLMs, the code generation. Step 3.
Iterative code generation. The engineer gives a natural language prompt, something like generate a system Verilog module for a 32-bit van der Korput sequence generator. The LLM spits out the code.
And the human refines it.
Iterates, integrates, and refines. This just cuts down on so many hours of tedious syntax and boilerplate logic.
Okay, but once that code is written, that's where the real danger starts. Yeah. How do you verify code from a model that can just make things up sometimes? This brings us to step 4, comprehensive verification.
This is maybe the most critical stage. It shows the LLM isn't just a coder, it's a full verification partner. It doesn't just generate potentially faulty logic, it generates the tools to find the fault.
How does it do that?
The sources highlight 3 key things the LLM creates. First, the complete system Verilog test bench structure.
So the environment for the test.
Yep. Second, it creates a whole suite of test cases to hit all the tricky scenarios and edge conditions. And third, and this is what really stands out, it writes a Python reference model script.
Wait a second. The LLM is generating the hardware code, but it's also generating the mathematically perfect external model to check its own work. Isn't that like the model grading its own homework?
That's the critical insight. It does introduce risk, but it also gives you this monumental efficiency gain. The Python script produces the golden sequence, the perfect output you expect.
So you run the hardware simulation.
And compare its output directly against that Python golden sequence. You spot any deviation instantly. The whisk is managed because the Python model is much simpler for a human to audit for correctness than the complex hardware code.
Ah, I see. It's a high-level independent cross-check. That makes sense. Okay, we've verified the logic. What's next? Step 5.
Performance optimization. After initial synthesis, the engineer looks at the results, how fast the circuit can run, how much power it's using. They can then leverage the LLM for suggestions.
Like what kind of suggestion?
Maybe suggesting pipelining to increase clock frequency or finding logic that can be shared to reduce the area on the chip, all to hit those power and timing goals.
And finally, step 6. The part every engineer secretly dreads.
Automated documentation.
If it can solve that alone, it's worth it.
It's a huge deal. The LLM generates detailed technical specs, user guides, even code-level comments, all automatically, pulling context directly from the design. It ensures documentation actually keeps pace with the design for once.
So we've gone from an idea to documented, robust hardware. But the real proof is in the performance. Did this workflow actually produce efficient, high-performing silicon?
That brings us to section 3. The proof is in the performance. The project implemented a full IP core with 6 different sequence types, which really showed the LLM's versatility.
What were some of those sequences?
They range from the simple van der Korput and Halton sequences all the way up to complex geometric mappings like circle, disk, sphere, and the grand finale, Sphere 3.
Sphere 3 sounds complicated. What's involved there?
It's a huge algorithmic challenge. It requires the LLM to understand and implement 4-dimensional spherical mapping to get a uniform distribution on a 3D sphere.
So it's integrating multiple base generators and doing complex math.
All under rigid hardware constraints. And the LLM managed that sophisticated implementation successfully.
And I notice a very specific requirement for the arithmetic.
Absolutely. To balance precision and efficiency, all calculations used 32-bit fixed-point arithmetic. And the sources note the LLM specifically recommended the Q31 format for this.
For our listeners who aren't deep in FPGA logic, what does Q31 format mean? Why is that recommendation so significant?
Well, it shows the LLM acting as an architectural advisor, not just a coder. Q31 is a specific way of representing numbers with a fixed decimal point.
To maximize precision without using up too much memory.
Exactly. It's a very hardware-specific decision, not just a coding choice. The LLM correctly advised on the best format for the job.
Let's get to the numbers. How did the simplest design contrast with the most complex one?
The results were great. Let's look at the extremes. The basic van der Korput generator fast and simple used a mere 500 LUTs.
LUT being the basic logic block on an FPGA.
Right. It achieved a blazing clock frequency of 200 megahertz, had ultra-low latency of just 3 cycles, and only used 70 milliwatts of power.
That's incredibly efficient. Now what about the heavy hitter, the Sphere 3 generator?
As you'd expect, it was more demanding. It used around 2,000 LUTs. But critically, it still hit a very respectable clock speed of 100 millihertz with a latency of 8 clock cycles. Power was still low at 150 milliwatters.
So the takeaway isn't just that it can write the code, it's that it writes code that is efficient, synthesizable, and ready for low power devices.
Precisely. It shows versatility across complexity scales while maintaining high quality, efficient results.
These metrics are fantastic, but we have to move to a more critical assessment. Where did the LLM really shine, and where did the human engineer remain absolutely indispensable?
And that's section 4, the balanced assessment. The LLM is a powerful accelerator, but the human expert is the ultimate firewall.
So, where were the biggest, most undeniable strengths?
Three main things stood out. First, efficiency gains, just radical acceleration in prototyping and a huge reduction in manual effort. Second, quality and consistency. The generated code followed best practices, which made it more readable and maintainable.
And the third,
Knowledge access. It was the ultimate on demand expert, instantly pulling up info on obscure algorithms or syntax whenever the engineer needed it.
but every new tool has its limits. Where did the experts still have to take the lead?
The limitations also fall into three clear areas. First, complex logic. The LLM really struggled with nuanced or intricate state machines. It often generated code that was buggy or just overly verbose, and it needed a human to come in and simplify it.
And second, this inability to innovate.
That's a crucial one, architectural innovation. The LLM was brilliant at implementing a human defined architecture, that blueprint from step 2, but it simply could not propose novel system architectures itself. It's just remixing what's in its training data.
And the third limitation, the one that probably keeps hardware designers up at night.
Accuracy and hallucination, you got it. Because it's probabilistic, it would occasionally generate code with subtle, deeply embedded bugs or just make factually incorrect statements. That demands rigorous, expert level human review.
Which brings up the inherent risks. If we start relying on these models for core hardware, what are the pitfalls we have to guard against?
Well, the first two are about reliability. Code correctness means a logical flaw could lead to a catastrophic failure in the final product. And then there's bias replication. If the training data is full of flawed designs, the LLM will just amplify those flaws
That's stifling innovation.
and locking the industry into subpar methods. But the most concerning risk, especially for critical infrastructure, is security.
Tell us more about this threat of hardware trojans.
A hardware Trojan isn't a software bug. It's a physical weakness embedded in the silicon itself. A few lines of code that create an unseen backdoor, a kill switch, a data leak.
And malicious use of LLMs could make it easier to hide these things.
It could simplify their insertion or even introduce new types of loopholes we haven't seen before. The risk is catastrophic in defense, or medical devices, or autonomous cars.
So if the tech is this powerful but carries this much risk, what's the mitigation strategy?
The framework is clear: human-centric quality control. You have to have mandatory, rigorous code reviews by expert engineers, and you have to integrate specialized security tools to scan the generated code specifically for Trojan signatures and other dangerous patterns,
So security has to be baked into the process from the start.
not bolted on at the end.
Okay, if we synthesize everything we've learned today, the efficiency, the risks, what's the core takeaway for the hardware engineering field?
The LLM is creating a new design paradigm. It's defined by a massive productivity leap through automation and something we could call knowledge democratization. It acts as an intelligent mentor.
So they aren't replacing chip designers.
No, they're empowering them to do more, faster, and to focus their human expertise on the highest value tasks.
It's an unprecedented tool for accelerating the implementation of a known architecture. We saw it translate complex math into efficient hardware based on a blueprint the engineer provided.
Which leaves us with a final provocative thought for you to explore on your own. Given that the sources all emphasize that LLMs excel at implementation but struggle with proposing novel system architectures, if a new generation of engineers comes to rely primarily on LLMs trained on our current best practices, how can we ensure the industry continues to produce truly revolutionary, never before seen architectures instead of just getting really, really good at optimizing the ones we already have?